So it's a pleasure for me to welcome Heidi Rzehak. Heidi is a German physicist, but she's been in different places. Among that, she's been 7 fellows, a couple of years, and then she was in different places before CP3. And she's going to discuss, enlighten us with the true nature of the Higgs boson.
Thank you very much. Yeah, so I will talk about the uncovering of the nature of the Higgs boson, but yeah, I hope that at the end of the talk, the title will be crystal clear. But before that, before really coming to the Higgs boson, I want to go back in time into the year 2008, when, so before the Large Hadron Collider actually started running. At that time, there was one of those Nobel laureate meetings at Lindau, where PhD students have the possibility to meet Nobel laureates. And at that time, it was kind of towards particle physics, and these 3 Nobel Prize winners have been asked what they would expect, what would be discovered at the NHC. And Toft said that he would think one would find a Higgs boson or more, so several Higgs bosons. David Cross was hoping to find a superworld. What that means, what is behind this superworld, we will see during the talk too. And Feldman was hoping for something unexpected. And you see a slight smile here on Toft's face. So, going a bit ahead in time, NHC has started running and had produced the first results. So we go to November 2011, and at that time there was the Hadron Collider Physics Conference, and the experimentalists showed new results where they excluded Higgs bosons for a certain mass range. So they can do their measurements for specific masses and kind of scan through the masses and say, okay, a Higgs boson with this mass is not there. So they excluded a wide range of the 6 masses, and you could hear theorists saying that, well, until the end of 2011, the Higgs boson will be excluded completely, so this mechanism would be dead. So, and then this picture changed dramatically 1 month later, in December 2011, where Atlas and CMS reported an excess of event that was compatible with some Higgs boson. But at that point, it wasn't clear whether it was really a Higgs boson, or since we are dealing with statistics here, it can always be that some other events happen more often than in average, and that it's just a sort of upward fluctuation. And so at that point, it was too early to draw any conclusions about what that is. But of course, some people will then say, yeah, that certainly is a Higgs boson, and some other ones say, oh, no, it will go away. And then in July 2012, Atlas and CMS announced the discovery of a Higgs-like particle. So they called it, at that point, they called it Higgs-like to really make sure that it somehow looks like a Higgs boson, but that you have to investigate further to really make sure that it is what we think of a Higgs boson. And that they did, and then in October 2013, the Nobel Prize was given for the theoretical discovery of a mechanism that contributes to our understanding of the origin of mass. And this is basically the Higgs mechanism, and you will see how these 2 things are related. So my plan basically for the talk is that we start here and really look at the Higgs mechanism and the Higgs boson, and how it was discovered, what we know now. And then I want to talk about standard model extensions and one property of the Higgs boson's mass. And then also from the perspective of extensions of the standard model, I want to look at other properties, the couplings. But yeah, I hope that this So let's first start with the standard model of particle physics. So this is, as it says, standard model. It's what we use to start with at the moment. And you have two types of particles, the fermions and the bosons, that differ in this certain property that is called spin. Oops. So the fermions have half spin and the bosons have an intentional spin. So just take it as a property of the particle that identifies this particle. And for the fermions that are also so-called the matter particles, we have quarks, the up and down type quarks, and then heavier partner, the charm quark, the strange quark, the top quark, and the bottom quark. They are basically copies of this first generation, as it's called, and they're just heavier. And then we have leptons, where we have the electron and the neutrino, and then again heavier copies of that, the muon and the tau, and the respective neutrinos. And the proton and the neutrons, they are built up of the up quarks and down quarks, and proton and neutrons make the nucleus, and then you need the electrons to build an atom. So basically, this is how our matter is composed and why it's called matter particles. And the forces between those particles are mediated via the gauge boson, the so-called gauge bosons, which are also sometimes referred to as interaction particles. There we have the photon, which is basically the particle of light, so the quantum state of light, so the electromagnetic interaction. We have the W-Z bosons for the weak interactions, and the gluons for the strong interactions that are especially important in the nucleus, where to keep the up and down quarks together. And these gauge bosons have spin 1. And then we have the Higgs boson, which is the only particle with spin 0. So in that sense, you see already that it's kind of special in the standard model. You have here spin half particles and here spin 1 particle, and then one that kind of is outside of all of that, because it's a spin 0 particle. Okay, now why do we have this Higgs boson? So our theories, they are based on gauge symmetries, and in these theories, if you have gauge symmetries, we realize that the gauge bosons have to be massless if the gauge symmetries are exact, so unbroken. But experimentally, we know that actually these gauge bosons have masses, so the W and the Z boson, they are massive. And here you see one of those mass peaks where you have a proton-proton collision, and a Z boson is produced and decays then into a pair of muons, and looking at the energy and the momentum of these muons, you can reconstruct this mass peak, and this is clearly non-zero. So if it has 0 mass, it would be shifted really to the 0 side. So it's non-zero. So one possibility, of course, would be to throw away those gauge theories, and the other possibility is to find an explanation within that. And the explanation is, or the idea was to have an additional field that is non-vanishing in the vacuum, so that you really have, in the lowest energy, even if there's nothing, there's still this field. So you cannot make less in your vacuum, basically. There's always this field. And this, to explain that in some sense, in 1993, Mr. Wellgrove, who was at that point UK science minister, asked for an explanation that he could understand, an explanation of the Higgs mechanism. And this is basically one of the explanations that were suggested. And you can imagine a cocktail party where the guests are uniformly distributed in the room. And this is kind of the Higgs vacuum field, so there are people everywhere. And then a famous politician enters into this room, and suddenly people gather around this politician, and this way this politician kind of acquires a greater mass than normal, and she cannot move as fast as before with the same momentum. And so in that sense, she in the picture is a massive gauge boson. So to describe it a bit more with physical quantities, so basically you have a field that has a potential. So if you are not used to this kind of notation, don't worry, you can basically look at these shapes of these two things. And yeah, basically if this parameter mu is larger than 0, we have the shape of this potential of this form. And there you can see the lowest value, which is the lowest energy value, is really at 0. And then there's basically no field at the lowest state in the vacuum, and the gauge bosons would appear massless. They don't have anything to interact with. And if this mu is smaller than 0, then you see that suddenly the lowest value is for non-vanishing values. So there is, even at the lowest state, there is some field. And then these gauge bosons interact with this background field and appear to be massive. So you can see it either way. Either you say the gauge bosons are basically massless, but interact with some background field, or you really say, okay, I don't know really about the background field, but yeah, I see a mass. So it's kind of two ways of seeing the same thing. So basically this interaction makes them appear massive. And now, of course, this is the Higgs mechanism, and you might wonder, well, what about this particle that we have been talking about before? So there's, until now, we had the background field, but we haven't had that particle. And basically the excitation around here is the physical Higgs field. And going back to the cocktail party, you can picture that with a rumor that enters the room, and again you have the uniformly distributed guests, and then the guests itself start to cluster, and the cluster moves around, and this is kind of an excitation of this uniform field, and it can describe a massive Higgs boson. So this is where basically the Higgs boson enters, and seeing this Higgs boson helps us also to connect the Higgs boson and the Higgs mechanism. And without this Higgs boson, this Higgs mechanism wouldn't be confirmed at all. So that's why the Higgs mechanism that was proposed long time ago, the Nobel Prize was only given for in 2013, after some of the properties of the Higgs boson had been explored a bit more. So now, how was it discovered? So it was discovered at the Large Hadron Collider in Geneva, and this is a proton-proton collider. And there are two to three main channels, I would say. So the one is that basically the two protons collide with each other, produce a Higgs boson, and decay then into Z bosons that then again decay into leptons. So here the example is basically for muons, and so basically the beam enters from here, so perpendicular to the slide, and the protons interact here, produce the Higgs boson, then decay into the two Z bosons, and then you see those red lines here, and these are basically the leptons that are the decay particles. And from measuring their energy and their tracks, you can reconstruct the Higgs boson and its properties. Another way is that the Higgs is produced and then decays into two photons, and this is here, basically. And as theorists, we picture it a bit differently. We rather picture it in so-called momentum space and use Feynman diagrams. And that is nice because you kind of see how the particles interact with each other. So basically for these two processes, the reduction process is the same, and what actually interacts is the gluons inside the protons, and they need some particles to help to talk to the Higgs boson, so these are the top quarks, and then the Higgs boson is produced. So this is the same on both sides, and then this directly decays into Z bosons and then these two leptons. And here the Higgs boson again doesn't talk directly to the photons but needs some other particles to mediate this interaction between the Higgs and the photons, and you see the decay. And there, for this channel with the decay into two photons, we have another channel. This is the so-called vector boson fusion process, where you have in addition to jets, jets are quarks and these kind of things that you see as these kind of lines. So you have here is the beam lines, so the protons come from here and here, interact, produce the Higgs boson, which then decays into those two photons. And then you see also two other tracks, and these are the two so-called jets. And here's the picture in Feynman graphs where you have a quark, those quarks from the protons interacting, radiating off some vector bosons that produce the Higgs boson. And here the decay process is the same as before, but you also see those two quarks as those two jets in the detector. Okay, now we have discovered that, and of course the question is it really the Higgs boson or is it something else? Is it the Higgs boson of the Standard Model or of an extension of the Standard Model? And so you go through the properties and look at the properties. So one property is of course the mass, but in the Standard Model it's a free parameter, so you just measure it and then you can see whether the relations between parameters that you can predict are consistent, but otherwise it doesn't really tell you anything whether it's a Higgs boson or not. But it's very well measured already. It's 125.09 and some statistical and systematic error, which is already quite small. And from measurements like the mass of the W boson, you would have expected it to be of the order of 100 GeV. Okay, then another property that I've been talking about before is the spin. And from the decay products, you know that it has to be a boson because of the conservation laws that are behind that. And then the spin 1 particle would be a possibility, but there is a theorem already. So already from the theory side, it says, well, a massive spin 1 particle cannot decay to two photons. We know that it has mass, this particle, and we know that it decays into two photons. So it's rather excluded, and experimentalists still tested it anyhow and found that this is rather excluded. Then they also tested a spin 2 hypothesis and also excluded that with more than 99% confidence level. And they found that the spin 0 is compatible, which we have seen before is the Standard Model prediction. And then the next property is the behavior under charge conjugation and parity transformation. So charge conjugation just changes the charges from plus charge to minus charge, and parity changes the spatial components, the sign of the spatial coordinates. But basically you can see it as another property without going too much into detail. And there are two options. It could be CP even and it could be CP odd, and the CP odd one is excluded with more than 99% confidence level, and the CP even part is compatible, and this is actually also the prediction of the Standard Model. So this also confirms a standard model behavior. Okay, I don't want that. It's very nice.
You can download the Higgs from the standard model, from the Apple store.
Yeah, you can download it.
So start.
Okay. And, oops. Uh-oh.
As you said, it's
Yes, thank you. So sorry for that. Okay, another property is how these particles interact with other particles. So that is what we call couplings. And those couplings you cannot measure directly. You measure basically the whole thing. You measure the production and the decay in one go. And I've talked already about the main discovery channels, and then there is another channel where the Higgs decays into W bosons, which also more involved in the discovery. That's a minor part, and this is compatible with the standard model. Then this Higgs boson can also decay into tau leptons, which was the heavier copy or the heaviest copy of the electron, and this is also compatible with the standard model. And further processes like the Higgs decay into bottom quarks are investigated, and yeah. Still, there are relatively large errors, like 10%, and not all couplings are accessible that way via just looking at these channels. And yeah, on this side, you see some signal strength, which is basically the measurement of these production and decay channels divided by the standard model prediction. And here in this picture, you see this dashed line is the standard model prediction, and the blue ones values are the values that Atlas measured. The red ones are the ones that CMS, the other experiment, measured, and the black ones are the combined ones. So they are lying more or less around the standard model. One further thing that I want to say about those couplings, one sometimes refers also to the Higgs boson coupling to the mass of the particles, and this is basically illustrated via these plots where you have the couplings of the Higgs bosons to fermions and bosons as a function of the particle mass here. Like here the muon, the tau, the bottom, and the W, Z boson at the top core, and they lie on a straight line. This is kind of this coupling to the mass, that the mass is proportional, that the coupling is proportional to the particle masses. Okay, now still we are wondering whether this is the Higgs boson and how looking at these properties can help us to say something about it. So first of all, this mass, which I said was just a free parameter in the standard model. In models beyond, it's not necessarily a free parameter, so using this value that we have, we can actually constrain other models and say, okay, and maybe even exclude them, but at least constrain them. And then, yeah, here I said before they are either CP even or CP odd, but that's, yeah, in the standard model, as I said, they are only, the Higgs boson is CP even, but it can be, if we have a violation of CP, as it's called, then one could also have a mixture of these properties. And finally, also these couplings, they could be affected by other theories, by an extended Higgs sector, we have more particles, or by other unknown particles, and of course the question is how much can they be shifted. Okay, now first I want to come to the standard model extensions and to the Higgs boson masses. But before that, maybe you are wondering at this moment, I've told you about about this Higgs boson and its properties, and it looked like more or less compatible with the standard model. And why should we bother to go beyond that when it's more or less standard model like so on. So I think it's still interesting to really dig deeper and see what actually the true model is, whether it's really the standard model only or whether not. And then beyond that, there are also reasons to search for beyond standard model physics, some coming from experiments like dark matter. So dark matter is matter that we don't really see. We only see that indirectly via the structural formation of galaxies and also rotation currents and these kind of things. So we think that there should be more matter than the standard model offers us, but we don't know what kind of matter that is. But there we would need to go beyond. Also, the asymmetry of matter and antimatter in the universe cannot really be explained in the standard model. We are all basically matter, and there's only few antimatter, which is good for us. But yeah, you also want to explain why this actually happens, and this is not really doable within the standard model. Another thing is that we know that neutrinos have mass, and it's not completely clear how that is really embedded into the standard model. So there also new physics could enter. So this is basically things really coming from experimental observations where we say, okay, this we don't really understand, and maybe we have to go beyond the standard model. And then there are also things from theory side, like grand unification, where that means that at a high energy scale we would think that we only have one interaction and not like the electromagnetic interaction, the strong interaction, etc., but just one. Then another problem of the standard model is that we only describe the electro-weak interaction and the strong interactions, but we don't describe gravity, and I mean gravity is pretty important, so at some point we would like to have a theory that includes that too. So this is something that is, of course, bothering theorists. And then, yeah, one thing is the so-called hierarchy problem, that the Higgs mass, if there is some physics at a high scale, is really sensitive to this physics at the high scale, which also is not very nice in the standard model. So these are the reasons to look a little bit beyond. And one possibility is to introduce a new symmetry. And this is one possibility is the supersymmetry, which relates those bosons, remember integer spin, and Fermat's half-spin particles. And they are, if there is supersymmetry, they are related via this symmetry. So now the question is, of course, how do we implement it into a model? Let's start to build a minimal model, the minimal supersymmetric standard model. Since this is really long, we just call it MSSM. And we start out with the standard model particle. So this is the particles you have seen before. And then one thing you need is a so-called second Higgs doublet in the MSSM, which gives you more Higgs bosons down here. So you have then 3 neutral ones and 2 charged, a negative and a positive charged Higgs boson. And you need those 2 Higgs doublets in the MSSM, for example, to generate masses to the up and to the down type fermions. In the standard model, you can do that with one Higgs doublet. So yeah, you don't need that, but the supersymmetry makes it necessary that you introduce the second Higgs doublet. And then of course you need superpartners. So you need partners to all the fermionic partners. These are then spin zero particles here, and partners to the bosonic ones, which are fermionic ones here. And yeah, then we have these nice namings, like this particle would be then an up squawk, so we would put an S, because those are spin zero particles and scalars would be squawks. And these particles, they are combined in a bit different ways and give then the so-called neutralinos, which are neutral, and the charginos that are charged. So we have more particles here. One further thing is, if we have really an exact supersymmetry, the masses of these superparticles and the masses of these particles of this side, they would be identical, and this is experimentally excluded. So we cannot have a model that is really exact in this supersymmetry. But we don't know how to really implement a mechanism to change that, so we do it rather explicit. And I just say we need some SUSY breaking, and the way we are doing it, we introduce many new parameters, which also reduces a bit the predictability of this model, because you have many more parameters that you can fill around. So this is a not so nice feature. But this is also because we don't have a good mechanism to really do that. Okay, and one further thing that I should say, depending on how you implement this model, you can get a lightest particle, a lightest SUSY particle, which is stable, and then this particle would be a good dark matter candidate. So just to connect to one of those problems that we have. Okay, now I want to go to have a side remark about, to explain a bit about leading order and next to leading order that I will use in a bit. But I'm doing it in a very mathematical way, and it's rather just to make it a bit plausible what I mean. So basically, imagine we have two towns or two villages, A and B, and we have two lakes here, and we want to walk from one to the other, and we want to know the walking distance from A to B. So if you really want to have a very rough estimate, you say, okay, just draw a straight line, and then you have a sort of approximation for your walking distance. And this I would now call leading order. And then you say, okay, maybe this is not good enough, maybe I should use two straight lines, and then I can do something like that, and that I would now call next to leading order. And what I will be talking about in the next bit is about next to leading order corrections. So this would be then basically the difference between this distance and the distance that I showed you before, so the bit that comes on top of it. But still, here you can say, okay, maybe this is still not good enough, maybe we should use 3 straight lines, and then we can already approximate it pretty well on our distance. So yeah, just to give you a feeling about how we try to approximate these kind of things. And now we hop back to the masses and to the Higgs sector and the MSSM. So I said already that we have these 5 Higgs bosons, 3 neutral ones, and 2 charged ones. And yeah, there we have 2 CP even and 1 CP odd. So they have also different properties than the standard model Higgs bosons. And the speciality of this model is that not all those masses are independent as in the standard model, but you have basically 4 masses for these particles. The charged masses, they have the same mass. I mean, it's just the antiparticles. And then you have 2 free parameters, so that means they have to be kind of connected, these masses. The lightest Higgs boson is often referred to the small h one, and if you calculate its mass, you realize that you have an upper theoretical leading order mass bound, so a leading order approximation that is at the Z boson mass that I showed you before, and this is 91 GeV. And now, if you think back, I showed you that the value of the Higgs mass was 125 GeV. So if leading order would be the right, really describing the complete theory, we could say, okay, throw this theory away, because 91 is just too low, we need the 125. But then we have higher orders that are the so-called quantum corrections, and they depend on those MSSM parameters, and then we can shift this up to about 140, so the 125 GeV is still possible, so it's still in the valid mass range. Okay, just why do we actually need this Higgs mass prediction at all? First of all, we need it as a consistent input if we want to have predictions within this model for the production and the decay of the Higgs bosons, and if we want to compare the measurement and the theory. And then, of course, we have this experimental measured value, and we can constrain the parameter space of this model. And to really precisely, or to really fully exploit this constraint, we really need a precise prediction. So already at the moment, the uncertainty of the measurement is by 200 MeV, while we would still say the theory error is about 3 GeV. This is 15 times larger than the experimental error. So yeah, it would be nice to know it much more precisely, to really use the precision that the experiment gives us. And it's already, this is the error that they expect to have, so they will reduce it a bit probably. Maybe they will do better than they have expected. And if we had a linear collider, it would be only 50 MeV. So now I try to explain you where those quantum corrections come from. So basically, we go back to the Feynman diagrams, and this is the leading order where we get just the leading order Higgs mass, and then we can have quantum corrections where we basically use this Heisenberg uncertainty principle that you cannot measure energy and time at the same level very precisely. So you can have this quantum fluctuation that you produce a particle and annihilate it immediately again, basically. And then you get these kind of corrections. Since this is one loop, it's one loop level, and since these are two loops, it's called two loop level. But this gives you then a shift of the Higgs mass. Okay, and now just a picture of such prediction for some parameters. So here you have the Higgs mass versus one of the parameters of the MSSM, the Stochastic parameter. And this line is basically the leading order prediction, so below 90 GeV. And then the blue line is the next to leading order, and the red line is the next to leading order correction. And here, these green lines basically give you the 125 plus minus 3 GeV. So basically, if you take the theoretical uncertainty into account, the band that is allowed. And so if you look at this curve and you say, okay, the red one is the most precise one, then you would say those parameters are allowed where the red line lies within those two green lines. Okay, so basically what you see, it constrains the parameter space, but it does not exclude it completely. So now the question is how much time do I still have?
Here, but 5 to 10 minutes left before discussions. It's almost an hour. You can also go a little longer if you want.
Yeah, but maybe I skip the next part here and just go to the deviations from the standard model. What I still wanted to talk about the couplings. So first of all, the question, of course, is if you look at the couplings, where can actually deviations come from? And I showed you before, when we were discussing the discovery channels of the Higgs boson, that some particles only talk to the Higgs boson via other particles. And basically, yeah, these couplings are then called loop-induced. And of course, if you have unknown particles, they could also talk or mediate the coupling between the photons and the Higgs boson and could change the coupling. So So this would be one possibility. Then of course, if you have an enlarged Higgs sector, it might be that there are, like I showed you before, there are two CP-even Higgs bosons, and that they just share the coupling that the standard model would have at all. So, and that would lead to some changes of the couplings that we measure. Then the third point is a little bit tricky. That is because we cannot, this wouldn't change couplings if we could really measure the coupling directly. This effect just comes because we cannot measure the coupling, but we always measure the production and the decay process completely. And there enters also an assumption on in which particles the Higgs boson can decay into and in which probability. And if you have additional particle it decays into, then these probabilities would change for the other particles too. And since of course overall it just can decay, so you have to add all the probabilities to get one. And that would change also the probability of the decay into W bosons or etc. So this makes it a little tricky and could change something. And this, I think, is meanwhile rather constrained. You could have two degenerate Higgs bosons that are really sitting at the same place, and then also change the coupling because they might couple a little different than the standard model. Okay, so then the question is, of course, can these couplings be kind of a window to new physics? So if there is no standard model physics seen at the LHC that is somehow related to our Higgs mechanism, how large are the deviations? And then the question is, can we actually measure precisely enough, and how precise we have to measure to actually see the deviation? So for example, if we measure with a 10% precision at the moment, but the deviation can only be 5% if you don't see anything else, then of course we are not sensitive to that. And in that sense, it also enters into the discussion, what kind of colliders do we need, what kind of detectors do we need to actually get the precision, to get at least this precision. And of course, it's always hard to answer these kind of questions, and it's not really one independent possible. So one can look at, we looked at 3 different models there. One is really a very simple extension of the standard model. You just have the standard model particles and one Higgs boson singlet, which gives you then in the end 2 CP-even Higgs bosons, where the lighter one we assume to be the standard model light one. And then the couplings are scaled with a certain factor with respect to the standard model coupling. And the question of course is how much can the scale factor be. Then there is the possibility that there are composite Higgs models, that we have standard model vector bosons and fermions, and we have a strong sector where particles interact strongly or weakly, and that this includes the Higgs boson. And then also, of course, there's the MSSM as one possibility. And then you can look at what is expected to be measured at the LHC, so the discovery potential of further particles. And because we're saying we're looking now at the deviation of the couplings if we don't see something else. So if we see something else, we already know it is beyond the standard model. But if we don't find another particle, it would be nice to know whether the Higgs couplings could tell us about whether we have some beyond standard model physics. And so it's important to look at the discovery potential of the other particles. And then also we have constraints from electron precision tests. So this is those measurements of the Z boson mass, the W boson mass that were already performed at lab. And from there we have a very nice set of observations observable set is very well known and constrains extensions of the standard model quite a bit. And here I'm just writing down how they are constrained. So this simple mixed-in singlet model is really constrained by the discovery potential of the other Higgs boson and by these electroweak precision tests. And these composite Higgs models, we found that they are really rather only constrained by the electroweak precision test, that they are much stronger than actually the experimental bounds of the discovery of other particles. And then we have the MSSM, where basically the discovery potential was the main constraining feature. So here you have two parameters of the MSSM. Basically, in the red area you would find other Higgs bosons, while in the green one you would only find one Higgs boson. So the deviations would be then in this area. Okay, and then what we found as deviations is in the mixed-in singlet case that we have a deviation of 6% for couplings to other particles, and like 18% for the coupling of the Higgs boson with itself. And for the composite Higgs model, the way we modeled it, we only have a precise number, rather precise number for the coupling to the gauge bosons of 8% deviation, and the other ones are like tens of percent. And in the MSSM, the deviations of the gauge boson couplings, they are really, really small. So they are less than 1%. So this is really small. And the coupling to the top quarks is about 3%. And then we have the coupling to the bottom quarks, and there we have 10%. If we look into a certain region of parameter space and don't see any superpartners, but we can even have 100% if we don't construct only look at tangent beta larger than is 20. And similar for this coupling of the Higgs boson with itself. And this, especially this, I mean, there we have quite large deviations, but it's really hard to measure this triple Higgs coupling. So it's I think about 20% or something that one can measure it. So it's really a challenge for the future to measure at least that precise. And these are really the maximal deviations. So if we don't see anything, then we are unlucky. We could have also smaller deviations. So now coming to the end. So I think it's really exciting that we actually found a Higgs boson, that there was a discovery. And I think it's still exciting to know what its true nature is. And at the moment, as I said, it's compatible with the standard model. We can constrain already parameter spaces of other models. So we can already use the properties, the measurements of the properties to constrain other models. And maybe if you look further into it and measure the couplings more precisely, maybe we can actually learn more about this particle and identify it better. And maybe this can really be also a window to new physics, so that we have some complementary to the direct search of the particles.
Heidi for a very clear lecture. So questions?
You said that the supersymmetry required 4 Higgs bosons.
Yeah, basically, yeah.
3 more, right?
Yeah. 3 neutral ones and 2 charged
And
ones.
2 charged ones.
Yeah.
And these, I didn't get into the masses of these extra Higgs bosons. Are they way above the 124, or are they the same? I didn't.
They can be above that, and they can be.
And even above what you can measure at the LHC?
Yeah, in principle, yes.
Okay, but they are distinct masses, so it's not like you can have 2 that are.
No, I mean they are related, those masses, so it's not that yeah, so they are, so for example, the mass of the charged Higgs boson and the mass of the secret Higgs boson, at leading order they are basically the same plus the mass of the W boson. So that also enters there, but there's already a relation there. So if the mass of one of these is really large, so if you say the secret Higgs boson mass is really, really large, then the charged Higgs boson mass will also be really, really large.
Okay.
Any further questions?
In relation to, you talked about the high order corrections to the Higgs mass. You had a plot in which there seemed to be still a significant difference when you went from the first order correction to the second order. So wouldn't it be interesting going up one order? It looked like if you possibly went up one order, yeah, exactly. It went up one order, maybe the red one dropped further below it, you would strain even more.
Actually, that in this case it's kind of going up and down. So I think if you really stay in this, how this calculation has been performed, it could be that the next order again goes up a bit too. So this is not really clear whether it goes up or down.
So you have tried going up one order for.
There are calculations for also in higher order, but yeah, it's always only also part of it. It's not. It's. I'm just saying here. It's next to leading order, but it's not even the complete next to leading order. There are still pieces missing also in this thing. I mean, yeah, also there the calculations are ongoing, but yeah, people are looking into them and trying to calculate it more precisely to also get down this theory error.
Other questions? I also have a question about the future colliders. I mean, you kind of say what the limits of LHC will be. So what kind of colliders will you build to actually test these? Test the self-governance of the Higgs.
Yeah, that's
That's what people are discussing now, right?
yeah, and I mean I think it's hard if you look at the values that they expect to have. I'm not sure. It's always I think it's always also a problem of the communities whether they are more conservative or not, because I think normally it was said that the LHC cannot measure as the Higgs triple Higgs coupling as well as, for example, a linear collider. But when looking at the expected uncertainties that they would find, it wasn't that different anymore. So I'm not.
So the new one, the new X colliders wouldn't actually improve on the current, on the
Yeah,
LHC,
a bit. I think a bit, but from what they. But I thought it was kind of surprising. So I'm not really sure whether maybe the one parts are a bit more optimistic than the other ones. So. But of course, yeah, it's also the energy. Yeah.
So what is your bet? A bet something. What would you bet on? I'd say coffee. No more than that. I will ask you this too. So that's your bet. So if you had to bet anything, I mean, a coffee or very modest betting, what would you bet on?
I think it's really, really hard at that moment, to be honest.
So let's say Susie, composite dynamics, Higgs, Thunderbolt. You have three possibilities, right? So where would you put yourself? Then we'll pause it on Twitter. So I won't put your name there. So Higgs. That was good Higgs. I'll put it down. Okay. What would you be in this thing?
So just.
It's okay to change, your mind if you're working so fast.
Well, at the moment I would just stick to what I've been mostly working on, and then I would say it's Higgs.
Okay,
Otherwise,
Susie.
yeah. It's really
But then we go around. What would you think? After the two. Higgs. Next. Oh, okay. It's very critical about everything. Now you have to think of something.
I don't know.
How you have to make it? You have to make it.
I still don't put the composite.
Composite. That's okay. Then I'll send it. Hey, guess where you going? Oh, you want this out? I mean, very easy. Is there another? Well, what do you want? Extra? We can also put other. Other. And this was that's what I'm saying. Unexpected, right?
Yeah. Can I change my mind?
I'm a development supporter.
It's fair if you want to change your mind. You want to be unexpected or unexpected?
Unexpected.
Unexpected.
What's your feedback?
Keep on. Unexpected. Unexpected. Oh, this you know.
Composite.
Composite. But once you didn't say composite, you're going to be fired after. So after that, no, abstain, abstain. Front and back now.
Unexpected.
Unexpected. Ooh, cool.
At the moment, for me, it's composite.
Composite. Susie! It might be biased as CP3, but. What do you think?
Probably unexpected.
Unexpected, okay. And you're my student? That's fair.
Super.
Sorry?
That's right.
SH?
Yeah, that's one.
Super King. Then to the next line. Claudia. You know,
Unexpected.
positive. Unexpected.
Unexpected. Clearly. I'm working on a tree notes, come on, what do you expect from me? It's always unexpected.
That's okay.
I think also unexpected.
Unexpected. Then you treat people all unexpected. They won't come fast.
I don't want to lose my job, so composite.
You already have a 3 years job with anybody, so you're not losing your job. We can technically find.
Higgs.
Higgs, yeah, finally. For the lovely Higgs. You might win the bet, at least. Right.
Pouring through Higgs.
One of these two?
The first.
Higgs. Oh, I guess they're not really.
Same.
Higgs. I'm not really asking you to justify it. Did I put all of it? Did I put all of it?
Higgs.
Higgs. Now we go from this side.
I have an open mind.
Huh?
I have an open mind. I don't know.
But you can't. I mean, you have to
Okay.
make a. Which one?
Susie.
Susie.
I think the open-minded people tend to use the Susie Higgs.
Oh, but this is like Churchill told the Baditans. Before the end of the Second World War, there were 40 million of fascists. After the end of the Second World War, there were 40 million of anti-fascists. It's the same thing. You know, once we discover, I say it so, right? Is it true? I mean, that's the way it is.
Unexpected.
Unexpected. My style, I'm not really that good.
I think we should expect the unexpected.
So unexpected. I think we're going to declare the winner very soon.
Actually, I would like to bet on a discovery.
Yeah.
And to discover it, there has to be something unexpected. It's not a discovery.
You guys are playing all very safe.
Composite.
Composite. Very good.
Unexpected.
Unexpected. This is, I mean, you're going to be famous, right? You're going to be
Also unexpected.
unexpected. Yeah.
Maybe we should publish these results.
We will. I mean, nowadays it's easily put on Facebook and Twitter. All you need to do to be published.
Also go for unexpected.
Unexpected, okay.
But it won't be me to check it.
No, no, that's okay.
Unexpected.
Unexpected. Wow.
Unexpected.
Unexpected. Almost I can start putting this I think we should also ask Maria. Huh?
Unexpected.
Unexpected. So we have a clear winner.
What about yourself?
It's about the basic and all of four of them. I don't really have I'm a bit more of that. But
Then you have to take Susie Higgs because the open-minded people
Yes.
took this. Susie Higgs.
I'm not against myself. I'm not against me. I mean, this is more scaramantic. I need to put myself in the Susie Higgs, right? So you cannot say I'm not open-minded. So I put the Susie Higgs so that. Okay, so we have 1, 2, 3, 4, 5 for the stellar molar Higgs. 1, 2, 3, 4 for the Higgs. 1, 2, 3, 4, 5 for the composite dynamics. And this 8, 12, 15 for the unexpected, right? So I think we should give yourself a hand and you move and now we will see 5 years from now where we stand. So you got it complete.
That was before the photo.
Yeah, you have the bias. No.
So I think, I mean, yeah, I'll take a picture of that.
It's a question for you.
And also a picture of you. And publish simultaneously so that we will know. You can't bail out from this, right? This is, that has to be visible, no? Okay. Heidi. You'll be part of it.
But you have to be part of it.
I cannot do
You can
that.
make a selfie. You can make a selfie of it.
I can make that.
It's over ready.
Okay, good. Fine. All right. I think shall we give a hand again to Heidi?